Welcome back for our next discussion in Chapter 7 on applications of integration. In this discussion, we are going to dive a little bit deeper into not just talking about area between curves, but stepping up the dimension to now talking about volumes. Specifically, we'll be looking at volumes of solids of revolution. And so what we will be doing is taking regions that we discussed in Chapter 7.1 and taking those regions, and instead of just finding the area between two curves, we will take the region and revolve it around some sort of axis that will be given, generating a three-dimensional solid, and we'll ask ourselves the question, what is the volume of the revolved solid? So solids of revolution is our geometric object we'll be discussing, and finding the volume of that region will be our goal. And so we'll start out, instead of getting into some theory, we'll start out with a little motivating example, because sometimes it's best seen through looking at a specific case. And so what we're going to do is I drew up a very simple region for us to start with. Our motivating example will be this nice triangular region in the plane. And so I have it bounded here by the curve y equals x. I have it bounded on the right side by the curve x equals 3, right, that vertical line at 3. It meets the origin at 0, so it pinches off right there, and bounded below by the x-axis, giving me this nice shaded region. And the goal is now going to be to revolve the region about the x-axis, so this horizontal line at 0, and find the volume of that solid. Now, we'll talk a little bit about what this shape is when I revolve it. It's actually a nice cone, right? It's actual cone. And the volume of a cone has a very specific formula. And so we could actually not use calculus at all and get out our geometry textbook and look up the formula for the volume of a cone. And you'll see that as long as you know the radius of that cone, the base of the cone, which we do, and as long as you know the height of the cone, which we do, we can find the volume of this solid without any sort of necessity of calculus. But if we change the structure of this shape, if we change the way that it looks in the plane, change the curves on which it's bounded by, we're going to need the necessity, we're going to need calculus in order to answer this question. But for right now, a motivating example, we'll do a shape that is somewhat familiar. Triangle, and revolve it, we'll get a cone. And so if I revolve this solid, we get a cone, but say it wasn't a nice geometric object, like a cone. And say I still want to answer the volume of this solid. Well, in that case, it would be very hard for me to understand the volume as a whole. And that's where the beauty of calculus comes in, because the idea of calculus is instead of thinking about the whole, you think about the infinitesimal, the small, the part, the piece. And then you bring all of those pieces or those parts or those infinitesimals together, gluing them together via integrals, the idea of integration, remember making the many parts one, and gluing the infinitesimals together, we make the whole. That's exactly what we did in the last discussion, finding area between curves. Instead of thinking of the area of the region as a whole, we just took straight line segments. We can measure the distance between 2 points, the length of a straight line. We can glue all of those straight lines together to generate a solid, or generate a region, right, an area. Same idea here. I don't want to think of this volume as a whole. And I'll apply the same principle that we did in the last discussion in 7.1. And for an arbitrary x value in this region, x, I'm going to look at a slice of this region, a straight line segment in this region. In general, what we're going to call this is a cross section. So we're going to find volumes by what we call the method of cross-section, some would say. So we're going to take a cross-section of my region. And instead of revolving the entire region, I will only revolve the cross-section. For right now, it's very important. I will make a note here. Cross-sections must be taken perpendicular to the axis of rotation. For right now, it will be a necessity that when we take a cross-section, a slice, that it is perpendicular to my axis of rotation. What do we mean by perpendicular? Again, remember, perpendicular means makes a 90-degree angle. And so if I have a horizontal axis of rotation, I need to slice my region vertically, take a vertical slice of my region. If my axis of rotation is vertical, then I would need to take a horizontal slice of my region. That's important because we're going to want to generate a certain type of shape. We'll talk discs or washers. And also importantly for right now, we'll talk about taking horizontal slices. When we take slices perpendicular to the axis of rotation, it tells us a variable we should be using. In this case, vertical slices, or vertical lines in general, are x equals lines, right? X equals 2 is a vertical line at 2. X equals 5 is a vertical line at 5. Vertical lines depend on x. And that means in my region, I would need to make sure that my variable of integration is x. Everything's written in terms of x. Why do I bring this up? Because, well, if I needed to take a horizontal slice of my region, that would happen if we were given a vertical axis of rotation. So if perpendicular requires me to take a horizontal slice of my region, horizontal lines depend on y, right? Y equals 5 is a horizontal line at 5. Y equals 0 is a horizontal line at 0. And so if I need to take a horizontal slice, that means I create a y dependency. It depends on the y variable. My bounds are then in the y direction. My functions need to be written in terms of the y variable. And we'll write all this out. But for right now, we just have the basic understanding. Okay, we need to take cross sections perpendicular to the axis of rotation. That's going to be our one requirement right now. And so we take a slice perpendicular. Instead of revolving the entire region, I only revolve the slice. And since I only revolve the slice, since I am only revolving the slice, it doesn't matter what the region as a whole looks like. A slice is always a line, and revolving a line will always generate a certain type of shape. In this case, if we revolve this line segment about that x-axis, in this case, I revolve, right? Imagine this line's on a skewer, and I rotate this axis of rotation so the line comes out of the board, goes back into the board, comes around the other side. It would generate a circle for me, a disc, we'll call it. And so if I look at the shape that's generated when I revolve the cross section, I get a disc. And instead of knowing the volume as a whole, let's just ask ourselves, what is the area of the disc? Well, the area of a disc, or the area of a circle, is pi r squared. Well, that would require me to know the radius of this disc. Now, the radius is very important, right? It's the distance between two things on a circle. So let's remind ourselves what a radius is. A radius is the distance from the center of a circle to the edge of the circle. So when I go to measure the radius of a circle, I need to know the distance from the center to the edge. Now, when I revolve this straight line segment, where is the center of my circle? Well, the center of my circle will always be the axis of rotation. It's whatever you are revolving about. Since I'm revolving about the x-axis, that's the line y equals 0, horizontal line is 0. My center is y equals 0. That's the center of my circle, the center of my revolution. Well, the edge of my circle lies on this curve, in this case, y equals x. And if I measure the radius, or the distance from the center to the edge, we're really just measuring the distance between 2 points. Now, we talked about that in 7.1, right? Measuring distances between points is subtraction, and it's always top minus bottom, larger minus smaller. In this case, the edge of my curve is larger than the center, so if I subtract in the right order, the radius in this case of this circle would be x minus 0. Right? Y equals x, y equals 0. The distance between these two curves is x minus 0, or just x. And so the areas of these discs is pi r squared. Now we found r in terms of x, pi x squared. Makes sense, it's not a fixed value, it changes. It's pi times x squared, and that's because of course, if I take x to be over here, we still get a disk, but a larger disk. If I take x over here, we still get a disk, but we get a smaller disk. You get a bunch of disks that depend on x. Now that I know the area of a disk, or a general disk between 0 and 3, now all I need to do is integrate all of these disks together. I need to glue them together. Add up these infinitely thin disks, right? Just like we did with the line segments in 7.1. And so what would the volume be now? The volume would be adding together, integrating, all of these disks, the areas being pi x squared. Well, I need a starting and stopping point, so x is going to start at 0 and end at 3, right? We have a starting value for x and ending value for x. I'm taking slices for all x values between 0 and 3. And I'm going to move along the x-axis, right? An infinitesimal distance along the x-axis. Add them all up, glue them all together. And this would generate the volume of the disk. Let's actually calculate it. Let's see what we would get. I can pull out pi. Remember, pi is just a constant, so we don't need to worry about pi coming into play in terms of integration. X squared. And it's a very easy antiderivative to take. We get pi x cubed over 3 evaluated from 0 to 3. And so what do we get? We get pi times 3 cubed over 3. One of the 3's cancel. We get pi times 3 squared. 3 squared is 9, and we get 9 pi. Of course, you would need to plug in 0, but I went ahead and bypassed that because, of course, when I plug in 0, I get 0 for the answer. And so 9 pi is what we get. Now, bringing this back to geometry, remember that we said at the beginning, when I revolve this triangle, you actually get a cone as a whole. You get something that looks like this when we glue it all together. Now, the volume of a cone has a very specific geometric formula. In this case, it's 1/3 pi r squared h, where r is the radius of the base of the cone and h is the height of the cone. In this case, you can tell me what r and h is. The radius of the cone, since we're on the curve y equals x, at 3 we're at 3. So the radius of this cone is 3. The height of the cone, right here, if you just look, is 3. So we would get 1/3 pi r squared times h. Well, 3's cancel. And what do you end up with? 9 pi. The same answer we got here via calculus, but of course we have a geometric formula to our advantage. Now, that being said, we're not always going to run into this scenario. It could be an abstract region, and in this case, calculus will help us. And so this is kind of a motivating example to get us the idea of what we're going to be doing. I'm going to change it up a little bit, make it a little bit more challenging, and then what we're going to do is kind of formalize this process. We'll write down some steps, get a more step-by-step method in order to calculate volume. And so I'm not going to change my region. I'm still going to keep the same region. The only difference is I'm going to move the axis of rotation, and this is going to change it a little bit for me. So now if I draw my same region in the plane, y equals x, 0 to 3. We have this nice shaded region here. And say now I wanted to revolve this about, say, a vertical line. And so say now I change the axis of rotation and say here is the x value 4. And I want to now revolve this about the line x equals 4. So the same question. Revolve about x equals 4 and find the volume. the idea is still going to be the same. We don't get quite a cone this time, and the reason we don't get a cone like we did in the last example is because there's this gap between the region that I'm revolving and the axis of rotation. So that actually when I revolve this region about this axis, I get like a hole in the middle, a cylindrical hole in the middle. And so the volume is going to be slightly different than the volume of a cone, but we can still calculate it. Instead of trying to think of the volume of everything as a whole, we will think of a single slice, a method of cross sections we call it. Now, the only requirement right now that we have is the cross section must be taken perpendicular to the axis of rotation. Now, this is important. Since we're revolving around a vertical line, we must take the cross section to be horizontal. Horizontal cross sections arbitrarily then depend on some sort of y value, right? I need to choose a y. A y value between what? Well, between 0 and what are my y bounds for my region? At 3, we're at 3, because y equals x. So instead of an arbitrary x value between 0 and 3, now I need to think of a random y value between 0 and 3 and make a horizontal cut at that y value. Since everything now depends on y, I would need to make sure that all of my functions are in terms of the y variable. That means this function here, y equals x, I'm not going to change the function, I'm just going to change its dependency. I'm going to solve it for the other variable, and this is why it's a motivating example, because it's not a difficult one to do. Solving it for x, we get x equals y. So instead of y equals x, we get x equals y. In general, we might have to move some terms around, add something, take square root, square both sides, something like that. But right now, right, solving this for the other variable, changing dependency isn't difficult. Instead of a function of x, we just need to rewrite it as a function of y. And it's not too difficult. Now that I've done that, we're going to apply the same principle. I take a cross section of my region. So I take my region, I take a horizontal slice, perpendicular to the axis, and I revolve that slice. Now in this case, when I revolve this slice, I don't get a disk. I get something close to a disk, but rather I get a disk with a disk removed, a disk with a hole in it. And so I get this type of shape. And say I wanted to know the area of this shape. We're going to call this shape a washer. Hence the disk or washer method is what we're going to call it. In the first example, we had disks. In this example, we're going to get washers. Circles with circles removed. Now, what is the area of a washer? Well, it's still circles. I just have a circle, and then I need to remove an inner circle. Right? Take the area of the large circle, subtract out the area of the small circle, would give me the area of the shaded region. It's just a geometry problem. And so we have two radii to consider. The big radius, we'll use capital R, and the little radius, we'll use little r. And if we subtract those two circles, we would get the area of the shaded region, where again, big R represents the large circle radius, and little r represents the little circle's radius. The distance from the center to the outer circle, the distance from the center to the inner circle. Now remember, what is radius? We need to find them. It's the distance from the center to the edge. So if we look at our picture, we need to measure the distance from the center. Now my center is not the x-axis anymore. It's the line x equals 4. This is the line x equals 4. And so measuring the distance from the center, which is at x equals 4, to the larger circle, the outer edge, well, the outer edge lies on the curve x equals y. Remember, we've changed dependencies. And so we would need to take the distance from the center to this edge. Now, being careful how we measure, again, distance between 2 points, you need to take bigger minus smaller. Now, when we're looking left to right, these are the bigger values, these are the smaller ones. So the axis of rotation comes first. So to measure this distance, it would be 4 minus y. So the outer edge to the center, that distance is 4 minus y. Your axis of rotation should always come to play in your calculations because the axis is your center and the radius is the center to the edge. Center is at 4, edge is at the curve y. The smaller radius, well, the center is still at 4, that's not changing, but the smaller circle, the inner radius, is on the curve x equals 3. And so it's the difference between 4 and 3. Instead of x equals y, it's x equals 3. And so the distance between 4 and 3, we see that is just a constant, in this case 1. You see that from the picture, right? No matter where I take my slice, that inner radius is fixed and is 1. Putting that together, now we know the area of a general washer for this region. And it depends on y, right? We're going to get different sized washers depending on the y value that you choose. And this is the generic thing we get. Pi times 4 minus y squared minus pi times 1 squared, right? The area of the large circle minus the area of the small one. Now that we know the area of a general washer in this region, right? If I move y around, we can still find the area of that washer, same formula. We now will integrate all of these together to find the volume. So I will add up all of these washers as we move along, not the x-axis now, but the y-axis, starting at 0 and ending at 3. Adding these washers up will generate the solid for me. And so I'll factor the pi out. Remember, pi is just a constant. We don't need to be worried about it. Don't forget to FOIL this out carefully, right? We get 16 minus 8y plus y squared. FOIL, right? First outside, inside, last. Minus 1. The 1's still there. 1 squared is 1. And then what we would need to do, let's go ahead and combine our constants. I'll write my y squared term first. Just write like a normal quadratic. 16 minus 1 is 15. So we get this polynomial, and at the end of the day, even though the setup was difficult, it's a very challenging shape per se, right? It's not a standard one. The integral we get to solve in order to find this volume actually isn't very difficult, right? We use the fundamental theorem of calculus now. We find our antiderivative. So this, again, just requires our knowledge of the power rule from Calc 1. We take our antiderivative, we plug in 0 and 3. We subtract them in the right order, so I plug 3 in first. So here we get 3 cubed, 27. 27 divided by 3 is 9. 3 times 3 is 9 minus, 3 times 3 is 9 times 4 is 36. Plus 15 times 3 is 45. So if I plug in 3, we get this. Minus, plugging in 0 though, gives me 0. So we always have to be careful, right? Try just for a second. Don't always assume you get 0, but we do. And then we just need to figure out what this is. And so we just need 9 minus 36 plus 45. And so what do we get? We get 9 minus 36, which is negative 27, plus 45 is 18. So we get 18 pi. So 18 pi is my answer. Don't forget the times pi. And so when we do this method, when we generate volumes using this process, this idea of cross sections, revolving the cross section, making sure that we take it perpendicular to the axis of rotation, we'll generate disks or washers for me, and this is the general process we have. Now to finish up this discussion before we do some examples, we're just going to go over to the other board and we'll look at a kind of step-by-step breakdown in order to evaluate these. So when we calculate volume using disks or washers, this is kind of the step-by-step process that we just did twice over, kind of written out for our knowledge. The first step is to know your region. Right, that's the first thing we did. We drew our region. I drew it for you, but you might need to draw it yourself. Know your bounds, your intersection points, right? What are the bounds of my region? Where does it lie in the plane? All that important stuff. If we don't know my region, I don't know the volume that I'm going to get. Know your axis of rotation. Is it a horizontal line or vertical line? That's important because when I take cross sections, I'm going to need to be perpendicular to that. And also that will determine the center of your circles, right? The axis of rotation is the center of the rotation. So when I'm measuring radius, it will tell me where the center is. The next thing is take a cross section. That's what we did. We took a cross section perpendicular to the axis of rotation. Again, very important. Makes a 90-degree angle. Once I do that, that will determine my variable of integration, right? In the last example, we had to take cross-sections horizontal, which means everything needs to be in terms of y. If I take a cross-section vertically, everything in terms of x. We need to change the dependency of the function if necessary. That's what we did in that second example. After we did that, we revolved not the whole region, but only that cross-section, only that line. And when I revolve that line, I'll get one of two shapes, either a disk or a washer. Really the same type of shape, right? It's a circle, or a circle with a circle punched out of it. One of two things will happen, disks or washers. I can find the area of those shapes. Now I'll need to find the radius, so that's going to require some knowledge, right? Distance between the center and the edge, the axis of rotation, and the curves. Once I measure the radius, I can find the area. Once I know the area of the disks or the washers, I can glue all them together or integrate those areas together to generate the volume of the solid. And this is the method or the process map that we will follow in order to calculate volume via the disk or washer method. And so that's where we'll wrap up our discussion today. In the next video, what we will do is take this into practice and do some more examples using this method, and then motivate out of it another way to calculate volume via this shell method that will come next. So I hope that was helpful, and I'll be talking to you guys soon.